So my name is J.D. Stillwater. I'm a science educator. I teach at the Circle School in Harrisburg, Pennsylvania. Pretty amazing little institution in its own right. But I'm here today to talk about science and spirituality. And I'm aware that when you talk about science and spirituality kind of in the same sentence, that a lot of us have in mind something like this, where religion and spirituality are diametrically opposed to reason and science. And that perspective is reinforced by this culture war that's going on in our country and around the world right now, where these two extremes trade insults with each other about the existence or not of a personal intervening God. And too often, they use a lot of bad language. I don't view science and spirituality as opposite ends of a spectrum. I think if there is a spectrum, this is the wrong one. For me, the spectrum lies between dogma and ambiguity, separation and connection, self-righteous conviction and mystery. The culture war is waged between hostile parties who both sit on the same end of this spectrum. I think that culture war is now obsolete. So 7 Candles is an invitation to dance over here. See, the problem with this old view is that science refuses to keep to its end of the spectrum. It keeps revealing things about nature that conflict with our religious beliefs. And spirituality refuses to keep to its end. For many people today, spirituality is more about becoming. It's a process of becoming. Spirituality as transformation. And there's this emerging synthesis around the world right now that's driven by the incredible success of the scientific endeavor and our deepest human longings for connection and for reverence with all that surrounds us. Theologians, even conservative ones, are looking at what science has revealed, and they're recognizing a transformative story that's as powerful as Scripture. And scientists are looking around at reality from quarks to quasars and experiencing a profound sense of oneness and joy and reverence, spiritual experience. So my purpose in this talk is to offer that science and spirituality are not only compatible, but they're mutually enriching. Science is about knowledge. It's a process for constructing shared models of reality, models that Hindus and Muslims and Christians and atheists and Jews can all agree on. And if contradictory evidence comes along, we agree to seek new models that fit nature better. Now the important words here are we and shared and agree. Science is a communal, transparent, global endeavor that all of humanity can work on. Spirituality, on the other hand, is an experience. It's an experience and a practice. It's a transcendent feeling of being part of something bigger, something profound, something sacred. Spiritual practice is about transformation, about becoming our best selves within that larger context, that larger integrated whole. Spirituality underlies the various religious traditions of the world, but is not the same thing as religion. Religion is our specific beliefs and rituals. Spirituality is a universal human experience. I'm not here this afternoon to sell you any new beliefs. Seriously. Whatever theology or spirituality or worldview you brought in here with is fine with me. That's why I can give this talk in a great diversity of settings. This is about how science can add to and integrate in with your own spirituality and your own spiritual practice. When I ponder the universe as science reveals it, I experience spiritual renewal. And it's that experience I want to share with you this afternoon. I encourage you to keep your own spirituality close by with you and see how it might mesh with what I have to offer. The 7 candles of my title are 7 revelations, 7 illuminations from science, each as profound as Galileo's revelation that the Earth orbits the Sun instead of the other way around. Very disturbing to the mindset at the time. Ready to go?
Yeah.
All right, let's dive in. First candle, scale. When we look up into the night sky, we see all these bright dots. Well, some of those dots, as you know, are planets in our own solar system. Sorry, Pluto, we do still love you. They're nearby, relatively speaking. Some of those bright dots are stars, like our sun, 1,000,000 times the size of the Earth. But the ones we call stars are much farther away. Some of them are thousands of light years away. Now let's pause and make sure we understand that a light year is not an amount of time, it's a distance. It's a unit of distance. It's how far a pulse of light can travel in a year. A year is a long time, light's really fast, so it's a long, long way. Some of those bright dots we see in the night sky are entire galaxies of stars. Here's an artist's version of our Milky Way galaxy, and as you can see, our sun, our solar system is out in the suburbs. We live in the suburbs of our galaxy, on a star that's insignificant enough to disappear in the haze of other stars out in that part of the galaxy. Here's some Hubble space photographs of other galaxies, other than our Milky Way galaxy. And what always strikes me about these photographs is how beautiful they are. They're just gorgeous. Other galaxies that we can see with our telescopes are millions or billions of light years away. From here we can see 100 billion galaxies with our telescopes. And on average they have about 400 billion stars each. 100 billion galaxies, each with about 400 billion stars. There are more stars in the visible universe than there are grains of sand on the Earth. Actually, it's worse than that. There's about 10,000 stars for each grain of sand on the Earth. Now, in the last few years, astronomers have figured out ways to detect planets orbiting other stars, to discover planets in other solar systems. And just in the last few months, their estimate went from, in the last 18 months, they had been estimating that there are about 150 billion planets in our Milky Way galaxy alone. Now they're saying 150 billion Earth-like planets in our Milky Way galaxy alone. And those numbers are just going to grow as we figure out new ways of detecting these distant solar systems. Now, when we say something is light years away, one of the implications of that is that when we look up, we're seeing history. Even light from our own sun takes a little over 8 minutes to reach us. So if the sun were to blow up, just completely explode right now, we wouldn't know anything about it for 8 minutes and 16 seconds.
Wow.
And then we wouldn't know anything about it because the next closest star to us is Proxima Centauri. It's about 4 light years away. So if some huge event happened in the Proxima Centauri system, like the star blowing up, the image of that event would take 4 years to travel through space before we would see it with our eyes or our telescopes, doesn't matter. So tonight, if you go out and look up and find Proxima Centauri, you're looking at stuff that happened 4 years ago. Okay? So when we look up, we're seeing history. Now, in the last decade, NASA has done a series of photographs. And the first one, and actually this is true of all of them, they pick a patch of sky that's really small, about the size of a grain of sand held out at the end of your arm, all right? And they choose a patch of sky that's black. There's nothing to see between the stars and planets and galaxies. And they open the shutter on the Hubble's camera, and they leave it open for a long time on the thought that if there is anything there to see, it's going to be really dim. So it's going to take a while to collect enough light to make an image. So sometimes they leave the camera open for weeks at a time. And then they close it and they see, what do you see if you look at nothing at all? Space between the stars. Want to see?
Yeah.
This is called the ultra-deep field. Light from over 10,000 galaxies. Every little dot on here is an entire galaxy of stars. And they find this in whatever direction we look. If you look at the blackness between the stars, you find this kind of density of galaxies. Light from there are 10,000 galaxies, by the way, in this image. Light from some of these galaxies traveled through space for 13 billion years before finally ending its journey in the Hubble's camera. If you want to look further away than 13 billion light years, or further back in time than 13 billion years, you can't. there's nothing to see. Because 13 billion years ago, the first galaxies of stars were just beginning to form. You're looking at them in this image. Now there's a phenomenon called redshift. It's a little bit like the Doppler effect that allows us to look at light from other galaxies, analyze it, and determine their speed and direction relative to us. And when we do that, we find that everything in the universe, no matter how close or far away it is, everything in the universe is moving away from us. Closer galaxies are moving away a little slower. The furthest ones are moving away very fast. And the ones in between are moving away, but at an in-between speed. So if you sort of paint a mental picture of this, make a movie in your imagination, it's kind of like a classic explosion, where everything is moving out from everything else. If this is us, close things are moving away, far things are moving away, but the further things are moving away faster. You follow that? So just for curiosity's sake, let's run the movie backwards. Well, in backwards time, everything in the universe is approaching us. The furthest things away are approaching the fastest, and closer things are approaching but a little slower. So if you extrapolate backwards from their current positions and speeds, you can figure out that 13.8 billion years ago, everything is right here. Everything in the universe, in a time backwards movie, arrives right here, 13.8 billion years ago. But I hope it's obvious that the universe didn't start with a watermelon. I love this movie. It started with a singularity, and I'll talk more about that in a little while. But the other difference between this movie and the universe is that there's no background to the universe. There's no setting that the universe takes place in. The universe is both the setting and the event simultaneously. And I'll talk more about that in a little while as well. Now there's a lot more to say about scale. I haven't said anything about dark matter and dark energy, and I won't go very far into it today, except to say that all we can see, all we know about in the universe represents about 4% of the total. The other 96% of the universe is this very mysterious stuff, very recently discovered, called dark matter and dark energy, two probably different things. I also haven't said anything about the other end of the scale, the very small scales of existence, the subatomic realm, but I'll touch on that a little bit in the fourth candle. So the essence of scale is that space and time are vast, almost beyond our ability to comprehend. Looking out is looking back in time, and if we look far enough, we can almost see the very beginning. And given the number of planets out there, we're probably not alone. Now, some people respond to this knowledge about the scale of the universe, both in time and space, by feeling really small and insignificant. For me, thinking about it carries me beyond thinking to awe and a transcendent sense of connection with all that beauty and majesty that's out there. Second candle, flow. Anybody know the compass directions in here? You should.
Yeah.
Which way is north? Everybody's pointing that way? All right, I'm going to just accept that. It's kind of, well, let's just assume it's the front of the store.
Yeah.
All right, little geography quiz, just play with me. Everybody point towards Canada. Come on, don't be shy. Point towards Canada. Good, all right. How about Oregon, Washington, that sort of western, okay, very good. How about Hawaii? All right, good. And how about China?
Either way,
You got it.
Yeah, China's that way from here, isn't it? Yeah. So even after 500 years of knowing that the Earth is a sphere, we still tend to think as though it were flat. So here we are about 40 degrees north of the equator. I think here we're about 38 maybe. I'm a little further south than my normal stomping ground. But I think you'll all agree that wherever you are on the Earth, if we had to define the word down, it would be towards the center of the Earth, right? People in South America and Australia, they're not upside down. Down is just towards the center of the Earth, wherever you go, right? Yeah? Unless you happen to be standing on the moon, in which case everything on the Earth is up, and now down is towards the center of the moon, right? If you're in a spaceship between the stars, how do you know if your spaceship is upside down? It's meaningless, right, at that point. So direction, especially directions like up and down, are relative. They depend on your location. They depend on your circumstances. So here we are, sitting in AFK books and records. If we were to try to sit as still as we can, are we nevertheless moving, whether we want to or not? You're nodding. Say more about that.
Oh, yeah, I believe we are because the Earth is rotating.
Very good. Yeah. Pretty fast. Even at our latitude, at the equator, it's 1,000 miles an hour. But here, it's about 700 miles an hour, right now, while we're sitting still. So that's our speed, right? We're done? No.
The Earth rotates around the sun.
The Earth is orbiting the sun. That's quite a bit faster. Yeah, that's right now while we're sitting here trying to sit still. But we could theoretically add the 700 miles per hour at midnight and subtract it at noon and calculate our actual speed right now, couldn't we?
No,
Why not?
because the sun's moving too.
Yes, we are orbiting the black hole at the center of our galaxy. That's a lot faster. Don't look at too closely, just make you dizzy. But again, we could calculate our actual speed by, figuring out the 86,000 and the 700, adding and subtracting, and find our actual speed right now, couldn't we?
Well, then you have the Doppler effect.
Right. Everything in the universe is moving. There's nothing that's sitting still. So speed is relative. It's always relative. You cannot find your actual speed because there's nothing that's holding still for you to compare your speed to. Even location is relative. Remember, if we run the movie of time backwards, everything in the universe comes back to right here. Cosmologist Brian Swin put it this way. He said, the universe does not expand into a pre-existing space. Space unfurls with the universe. This is very hard for me to get my head around, so it wouldn't surprise me if others struggle with it too. So I have another analogy that may help. We're going to let the rubber of this balloon represent space. So we've collapsed the 3 dimensions of our space down to the 2-dimensional thin film of rubber in the balloon. All right? So if you want to travel from one galaxy to another through space, you have to be like an ant crawling on the surface of this balloon. You follow that? So we're going to pretend that each of the stars on here is like an entire galaxy of stars. Now, space expands, the universe expands, because space itself expands, like this. So if you pick a star on the balloon, I'm going to let a little air out. Pick a star anywhere on the balloon, doesn't matter which star you pick, to represent us, our local group of galaxies. All right? As space expands, and I put air into the balloon, you'll notice that all the other stars move away from the one you picked. And the ones that are furthest away move away the fastest. So watch. You see that? Everybody follow that?
Mm-hmm.
All right, so once again, let's let time go backwards. In backwards time, all the stars are approaching the star that you picked. The furthest ones are approaching the fastest, just like in the universe, until we get back to the beginning. But the universe didn't start with a watermelon or a limp balloon. When you get to this point in backwards time, the laws of physics dictate that the whole thing collapses down into what's called a singularity. A singularity is infinitely dense. So the singularity at the beginning of time, everything in the universe, all the matter and all the energy were compacted down to a single point, occupying no volume of space at all. No height, no width, no depth. One single thing, infinitely dense. Now, let's start time in the forward direction again. And this is where we find ourselves in an expanding universe. But I have an obnoxious question for you. Which point on the balloon is the center of the universe? Wherever you are. They all are. You could argue just as validly that none of them are. Both of those opposing viewpoints are perfectly true simultaneously. I prefer to think it's wherever I am. You can too, if you'd like. So, distance, speed, even space itself, all are flexible, all are relative. They depend on various things. And Einstein showed us that time too flexes and flows depending on our speed, which we can't know in any absolute way. The essence of flow is that there are no anchor points in our universe. All is motion, all is process, all is flow, even time and space themselves. Everything in the universe began as one thing, and the center of the universe is wherever you are. Let's try not to let it go to our heads too bad. So in the past, my spiritual life was about looking for answers, some beautiful rock that I could cling to that would make everything make sense. Now, God for me, or ultimate reality as I call him, her, it, is a buoyant river with no shore, an inherently mysterious process of unfolding that I get to be part of for a while. Third candle, stardust. So in the beginning, when that singularity first made its presence, first had a presence, it only had energy in it. There was no mass yet. No matter, no mass, no space even. No solids, liquids, or gases. Just pure energy. So there was nothing there that we would call a thing. Pure energy, and that's it. Now, matter and energy are a little bit like nouns and verbs. Matter is stuff, things, objects. Energy is movement, action, ability. So how did the universe make all this stuff if all it had to start with was energy? How do you make nouns if all you have is verbs to work with? Well, it turns out, Einstein showed us that at extreme energy densities, if you get enough energy in a small enough space, a small enough volume, really compact, matter can actually condense out of pure energy. It's like something from nothing. Energy is not the same as nothing, but it's not a thing either. It's not an object. It would be like making diamonds from smoke. What had happened in the first moments after the Big Bang? Particles that would later form atoms of hydrogen and helium condensed out of pure energy. Now this is worth pausing and contemplating a little bit. It really is something from nothing. It's a miracle. It's a scientifically described miracle, but it's no less miraculous because we understand that it happens. So the early universe had elements of hydrogen and helium, had atoms of hydrogen and helium, but that's it. None of the other elements on the periodic table, none of the other stuff that makes up what we work with and interact with every day. You can't even make water if all you have is hydrogen and helium. So where did all this other stuff come from? Well, fusion in stars is one possibility. Our sun is hot enough that nuclei of hydrogen atoms, which have just one proton, can smash together and stick and form helium atoms. And then a helium and a hydrogen can smash together and stick and make lithium atoms. And so on, building larger and larger atomic nuclei on the periodic table of, the natural elements, up through iron. But that's as far as our sun can go. It can't make any elements larger than iron. And our sun, at the end of its serviceable life, is going to expand, and then it's going to contract again, and all those elements up through iron, from hydrogen to iron, are going to end up hanging out in the core of the sun until the end of time. They're never going to be made available for forming new planets like the one we live on. But there are some stars, some very rare supermassive supernova stars, they're called. They have to be at least 10 times the mass of our sun, which is almost incomprehensible. And those stars, at the end of their serviceable life, they get kind of hollowed out and they implode, they collapse spectacularly inwards. And when all that mass of that supergiant star collides at the center of the star, energy densities are high enough to synthesize or to fuse all the other natural elements that we find in the universe. Just in moments, They're made. And then the star explodes spectacularly outward, sending all of those elements out as hot dust into the surrounding space. Huge amounts of space. When a supernova star explodes, it's brighter than its entire galaxy, often. Huge explosions. And that hot dust gets spewed out into the surrounding space, and over millions of years, gravity can collect it back together to make new solar systems and new planets like the one we live on. So what this means for us is that somewhere near here in this region of our galaxy, about 7 billion years ago, a supernova star imploded, made all the elements that are here in this room, and then made them available for forming new planets. You could say that star's death gave us life. So if our bodies and all the other stuff in this room are made of pure energy from the Big Bang, you might be wondering, how much energy are we talking about? How much energy is residing in my body? Well, it's E equals mc squared. You just put your mass in for m. Calculation's not difficult, but the answer is astonishing. It's a lot. There's a lot of energy. It could be destructive or constructive. We get to choose how we use it. There's a lot of energy sitting in matter. And it's the same energy that exploded into being at the beginning of time. The essence of stardust is that your body and everything else that we would call a thing is a condensed form of pure energy, and lots of it. Energy that was explosively forged into matter at the beginning of time and then in the furnace of a dying star about 7 billion years ago. You are the universe, made of itself, but now aware of itself through you. The spiritual implication of stardust for me is that the seeds of you and me were present at the dawn of time, and we're descended from stars just like those we see in the night sky. Talk about noble blood. This body is one stage of our long, sacred journey together, from pure energy through now to pure mystery in the distant future. Fourth candle, nothing. So, we're made of atoms that were constructed by supernovas. What do you know about atoms? Probably picturing something like this. Protons and neutrons in the nucleus, a bunch of electrons kind of zipping around the outside. Yeah? Well, it's a nice model for chemistry. It works well to make some kinds of predictions, but they're not really like this. It's a gross oversimplification. So, to get at what atoms really are like, let's start with just a hydrogen atom, which has one proton in the nucleus and one electron sort of orbiting around the outside. And let's blow that proton up. Let's scale it up so it has a mass similar to a shot put or a cannonball. We're talking about a grapefruit-sized hunk of iron, all right? At that scale, the electron zipping around the outside in our atom would be the size of a BB, but it would be a mile away, orbiting around. So let's apply the same scale to an iron atom. Picture 56 cannonballs in a pile here on the floor, all right? And then a mile away, in several different directions, there are 2 BBs zipping around. 2 miles away, 8 more BBs. 3 miles away, 16 BBs zipping around. Pretty small, pretty far away. But then, in several different directions, 7 miles away, there's another pile, or several more piles, of 56 cannonballs that represents the center of the next atom, the neighboring atom in a chunk of iron. Right? What falls between, or what lies between this chunk of 56 cannonballs and the next one 7 miles away, besides those BBs zipping around?
Attractive forces.
Empty space, essentially. As far as things that we would call things, it's empty. There's nothing there. So even solid iron is mostly empty space. But I misled you by showing you pictures of cannonballs and BBs, because subatomic particles are not things. They're phenomena. They're events that act like things, but they're not things. Let me show you. This is a classic quantum physics experiment. Don't worry, you don't have to know calculus to understand this. It's really actually fairly simple. You take something opaque like a piece of foil, gold foil or aluminum foil, and you make a very thin slit in it, say with a sharp razor. And then you shine a laser beam on the slit. I have exaggerated the slit so you can see it here. But a very fine slit. And then you put a screen on the opposite side of the room just to see, what happens. And you might expect, very reasonably, that you would get a bright laser spot on the opposite wall. But that's not what happens. If the slit is narrow enough, the light diffracts or bends around the edges of the slit and goes out in all directions. So what you get on the screen is the brightest area is in the middle, opposite your slit, but then it gradually dims towards the edges. And no matter how wide you make your screen, some light will still hit the very edges because it's going out in every direction. You see that? Now when we're talking about a laser beam, this all makes perfect sense because we know that light has wave properties. It behaves like a wave sometimes. And waves do this. Sound waves do this, water waves do this. If there's a gap in a jetty, you can see this exact effect in a pool or in the ocean or whatever. Maybe some of you have seen this. But let's make things a little more interesting. Let's put two slits side by side and shine the same laser beam on the slits. Now light goes through each of the slits, but as it spreads out, the two different sources interfere with each other. So where you have two crests of a wave or two troughs of a wave, you get bright light. But where a crest and a trough get superimposed on one another, they cancel and you get darkness. So now what you see on the screen is not two bright laser spots that you might expect, but alternating bands of light and dark, where the waves interfere constructively and destructively. You follow that?
Mm-hmm.
Again, if we're talking about light waves, there's nothing surprising here. Well, not too surprising. This is to be expected when it's waves we're dealing with. But you can replace this laser beam with a cathode ray, a beam of electrons, or a beam of protons, or neutrons, and the same thing happens. Physicists have been able to shoot a single electron, just one of those BBs, at a double slit setup. And the electron, the BB, goes through both slits, interferes with itself, and makes the same pattern on the screen. They can't be little balls. They can't be little objects. There's something far more mysterious than that. Now, I have barely scratched the surface of modern physics. It gets weirder. It gets a lot weirder. But the essence of nothing is that the things we think are most real, most tangible, most solid, like iron, are by their very nature more like phenomena, stories, processes, energy. Matter, even now, is made of verbs, not nouns. Now, pop culture paints this image of New Age people as, space cadets sitting in a lotus position and maybe saying something like, I am a being of light. But however people might smirk, it's true, we are beings of light in a very hard-nosed scientific way. So how would our spiritual lives be different? How would they change? If we thought of ourselves, if we pictured ourselves on a daily basis, not as objects, but as a wild dance of ancient and mysterious energy, which we are. Fifth candle, evolution. The process of evolution is actually fairly simple. Darwin's insight had four basic ideas, four tenets. The first is that there are more offspring born in each generation than will survive to have offspring of their own. Those offspring are not all clones of one another. They vary, they're different. We look a little bit like our siblings, but we're not all identical twins. Those variations can be inherited. We look a bit like our parents, and our children look a bit like us. So those variations get passed on. This is my daughter, if it wasn't obvious. Since we know that not all of the offspring are going to live to have offspring of their own, and they're all different, and those differences can be passed on, any differences that give us an edge or put us at a disadvantage, well, the ones that give us an edge will be passed on to our offspring, and the ones that put us at a disadvantage are less likely to be passed on to our offspring. And if you apply these same ideas over many, many generations, you might expect that, for example, if it's better to be larger when you're a horse, we would expect horses to get larger over many generations, because the large ones are more successful at having their offspring grow up to have offspring. And that's exactly what we see in the fossil record. Horses used to be the size of cats, and now they're big enough to ride on and pull Budweiser trucks around. Shorter generations makes for faster evolutionary change. So right now, as we sit here, almost all of us have our skin covered with a bacterium called Staph aureus, Staphylococcus aureus. It's a good guy. We want it on our skin. It helps keep other bacteria off, the bad guys off. But if you expose Staph aureus to dilute or intermittent antibiotics, in a matter of a few weeks, it can evolve into something more like MRSA, methicillin-resistant Staph aureus, which can be deadly. So what does all this mean for us? Well, we're here because our ancestors survived to produce us. And they survived because they had what it took at the time they were alive. Traits which they passed on to us. So those traits, all of them, make us who we are. Even the ones we may not appreciate very much about ourselves. So what are your icky traits? Vanity, lust, rage, ambition, addictions. Maybe some of these sound like sins to you. Whatever we choose to call them, these are traits that our ancestors needed to live long enough to make our existence possible. And if they're not suited for our current environment, if we don't want them, then let's learn to control and manage them. But what if we began that process with gratitude instead of shame? There's another implication for us in this evolution thing, having to do with death. We are programmed to avoid death ourselves and to grieve the death of those we love. But consider for a minute, the flip side of our ancestors' survival is the necessary death of our evolutionary aunts and uncles, like the dinosaurs. We wouldn't be here if they hadn't made way for us by dying. We too will someday make way for something new by dying. We live by eating, which necessarily means killing. When you bite into a fresh apple, the cells of that apple are alive until you ruthlessly and viciously shred them with your pointy teeth.
Great.
Does this make you a horrible, vicious predator? I'd say no. I'd say it means that life and death are inseparably connected. Stars die and their ashes form new planets. Plants and animals die and their bodies make our bodies. Endings are also beginnings. Death is necessary. And from a really big picture point of view, death can be beautiful because it's an essential ingredient of life. Can't have one without the other. Now, I'm not going to go too deep into the story of evolution because you've seen it on the Discovery Channel and there's lots of other places to learn about that. But I do want to touch on 4 really significant milestones in that story. And I do so because there's a misconception out there that evolution is only about competition and survival of the fittest. And those are part of it. But I hope you'll see that some of the biggest leaps forward evolutionarily have come about as a result of profound cooperation. So the first big milestone is that life began. We don't know if it began here or somewhere out in space and traveled here. But what we do know is that at some point in history, non-living things, atoms and molecules that were not alive, came together in some kind of cooperative arrangement to form the first bacterial cells, the first archaic bacterial cells. Here again, it's worth pausing for a minute and contemplating on this. Living from non-living. It's a little bit like matter from energy. It's a wow event, not your everyday occurrence. It's a miracle. And this miracle is not yet scientifically described. We may get there. I assume it will happen sometime, hopefully in my lifetime. But it will be no less miraculous once we figure out how it happened, if we figure out how it happened. The next big milestone, and this happens to be my favorite one, is some of those ancient bacteria took up residence inside their neighbors' bodies. And we know this happened because bacteria only have a membrane around the outside of each bacterial cell. But your cells and every other living thing on the planet that's not a bacterium has membranes within membranes. Your nucleus, where your human chromosomes live, is surrounded by a membrane. You also, these green things are representative of the mitochondria. There are lots of other subcellular organelles, they're called, that have membranes around them. But I want to call out the mitochondria in particular, because the mitochondria, by the way, they're the powerhouse of the cell. That's where sugars get turned back into energy so you can do stuff. But the mitochondria have their own DNA, separate from the human chromosomes in the nucleus of your cell. They're little ringlets of DNA, just like bacterial DNA. So at some point in early history of living things on this planet, some bacterial cells started cooperatively living inside other bacteria, and that's called the eukaryotic revolution. Anything that descended from that event isn't a bacterium, but it does include every other kind of living thing on the planet. The next big milestone is that some of those eukaryotic cells clumped together in cooperative arrangements to become multicellular organisms. And this allowed for specializations. Now suddenly you can have tissues and organs where you can't with a single-celled organism. And the last big milestone is that some of those whole eukaryotic multicellular organisms began to cooperate together in groups, in societies, that in some ways act like individuals, even though they're made up of lots of individuals. And obviously it's not just people that do this. Now recently the word evolution has begun to be used to refer not just to the history of living things on this planet, but to the entire cosmos. And when we use the word this way, we see ourselves as part of a great story. A story in which energy evolves into particles, which make up atoms, that bond into molecules, that then coordinate to make cells, that cooperate in ever larger associations. You could say all of this is evolution. Does anyone see a pattern emerging here?
Complexity.
Yeah. As time goes by, the complexity of the most complex system in the universe increases. Now when I see a chart like this, I want to go right up here. I want to know what's next. What are we going to do next? And statisticians have a saying I love. It goes, prediction is difficult, especially if it involves the future. But we could guess that if this pattern continues, whatever is going to come next is going to involve more cooperation, whole new scales of cooperation that gives rise to new levels, new scales of complexity. But one thing we can be sure about is that until time ends, evolution is not finished. We're not the end of any story. We're the middle. The essence of this fifth candle is that we are survivors. built from blueprints slowly refined by our ancestors' continued existence. We could choose to be grateful for all our virtues and our vices because they made our births possible in the first place. And in the continuing evolutionary process, death is a gift from the past that we will each in our turn pay forward. Now, I inherited some serious guilt and shame from my Western culture. Maybe some of you did too. Along with some pretty twisted notions about cooperation and competition. Never mind the whole topic of death. Today, my spirituality involves trying to see some of these things from a deep time perspective, from a long-range view over time, or if you will, from a God's eye view. Sixth candle, emergence. So, here we are in the middle of the evolutionary story, but who's we? What do I mean when I say I? Am I just a collection of atoms? Are we just ping pong balls bouncing off one another? Are we soups of molecules, just chemistry, operating according to the laws of chemistry, bonding and unbonding? Are we just colonies of cells, like corals, each cell trying to live out its own destiny, oblivious to the human being? Well, I would say each of these phrases is true, but for one word. We are made of cells, which are made of molecules, which are made of atoms, but there's nothing simple or obvious about any of that. Something made from nothing. Molecules orchestrating their own replication. Trillions of amoebas cooperating to play the saxophone. The saxophone player only emerges when the cells, the molecules, and the atoms, each a miracle in their own right just for existing, are arranged in a very particular and precise way. And then, suddenly, the whole becomes greater than the sum of the parts, and we hear sax music. Similarly, a pile of steel and plastic isn't going to get you very far unless it's shaped and assembled just so. And a car doesn't assemble itself. You did. And the human body is far more complex than a car is. And it brings with it uniquely human emergent properties, like poetry, or logic, or faith. Emergence happens when new scales of complexity give rise to new properties. So, for example, hydrogen and oxygen share some electrons, and now, where before you had two separate atoms, you can have oceans, and rivers, and clouds, and thunderstorms that you couldn't have with just hydrogen and oxygen separate. Some cells cooperate together to make a multicellular creature, and before long you can have senses, and flight, and sexuality, and consciousness. Some primates start living in groups together in the woods, and soon there emerge language, and culture, morality, governance, religion, technology. At each of those transitions, there are three principles that we're operating. Cooperation provides a competitive advantage. Simple things come together to make more complex things. And then new properties emerge that weren't even possible before. We would say the whole is greater than the sum of its parts. In some cases, far greater. Like you, the universe is self-assembling. Your body is the cutting edge of self-assembling complexity in the universe. Einstein said it like this. How often do you hear scientists saying things like that in today's polarized society? But they think it. The essence of emergence is that cooperation and competition work together to increase complexity. And that brings new emergent properties that were previously impossible. You could say the universe is creative. For me, now, spiritual devotion is measured by my efforts towards a future with more cooperation and creation. and less divisiveness and destruction. Simple as that. Last candle, number 7, 1. Everyone play with me. Take a deep breath in and hold it. And while you're holding it, see if you can guess how many air molecules you just breathed in that were also breathed in by Moses. Go ahead, you can let it out. I'm not trying to asphyxiate anyone. This is a fairly common chemistry assignment in college freshman chemistry classes. You make a few assumptions. The calculation's not that difficult. But here again, the answer is somewhat astounding. Every time you inhale, you breathe in hundreds of millions of air molecules that were also, at some point, in the lungs of Moses, of Gandhi, of Stalin, of Joan of Arc, of Hitler, Harriet Tubman, everyone who has ever lived. Every animal that's ever lived, every plant that's ever lived on this planet. They're all right here in the atmosphere of this room. Speaking of plants, you may remember that photosynthesis allows plants to make themselves, to make their bodies out of carbon dioxide and water and sunlight. So, indirectly or directly, we are made of carbon dioxide and water. So let's take a closer look at those two things. This is a diagram of the water cycle. You've probably seen something very like this before, and you know the story. Water evaporates from the ocean, goes up into the sky and forms clouds, which drift over the land, and then it rains or snows or somehow precipitates down, and sooner or later, through lakes and rivers and ponds, it finds its way, or groundwater, it finds its way back to the ocean. But there's something missing from this diagram, and it's missing from just about every water cycle diagram I could find. Us. It's us. We are one of the things water does as it goes around its cycle. Water spends some time being clouds and glaciers and all that stuff, and some time being us. Every sip of water or coffee or any other aqueous beverage you take contains water molecules that have recently been things like thunderstorms, waterfalls, glaciers. Water comes alive when we drink it. So that's water. What about carbon dioxide? Well, carbon dioxide has a cycle too. It's called the carbon cycle. But in addition to spending time being living things, carbon dioxide spends some time being things like seashells and coal and limestone, concrete. Some of the carbon in your body right now this afternoon was a fresh apple last month, and some of it was gasoline in your car last winter. And now it's you. It's being part of you. Something similar is true with the nitrogen cycle, the oxygen cycle, the phosphorus cycle. All the elements that go into constructing human bodies have cycles. And the atoms spend time doing different things, and then they spend time being you. Every year, 98% of the atoms in your body get exchanged for new ones. But exchanged with who or with what? With everything. Everything in your surroundings. Your body is like a standing wave on a river. Matter moves through you, takes your form briefly, and then moves on to be something else for a while. So where do you stop and other things begin? Can you draw a meaningful boundary around yourself and say everything inside of that is me and everything outside is everything else? Well, skin seems like a meaningful boundary. You know, I'm inside my skin, right? Except remember, your skin is covered with staph aureus. They're kind of like part of you. You need them. And it's not just the outside of you, it's also the inside of you. On and inside your body, bacterial cells outnumber your human cells 9-to-1 because they're so much smaller and so much more numerous. There are thousands of species of bacteria living in and on you. Trillions of bacterial cells, all of them cooperating and competing with each other and with your human cells. They digest our food, they protect our inner and outer lining, and microbiologists are finding recently that they influence when we're hungry and thirsty, our food preferences. And most recently they're finding that the species of bacteria living inside you have a strong influence on your weight and even your emotions. So is it me who loves cheesecake or we? Good stuff. So I want to say a little more about those mitochondria, those remnants of ancient bacteria still living and operating in the human cells inside your body. As I said, they have their own little ringlets of DNA, and you got all of yours from your mother, who got them from her mother, and so on. They're inherited. Your mitochondria are inherited matrilineally. And paleogeneticists, that's a new field, paleogenetics, they've been able to use the known mutation rate of mitochondrial DNA to determine that every human being alive today is descended from one woman who lived in Eastern Africa only about 200,000 years ago. And this is National Geographic's map of how humans got from Eastern Africa to populate every continent on the globe. 200,000 years is not that long ago. Every human being alive on this planet today, regardless of race, gender, ethnicity, we all share a common grandmother. So look around at the people in this room. These are your cousins. There's only one family of human beings on this planet. And it's not just people. We share half of our genes with bananas, for goodness sakes. All the living things on this planet are related. We are part of a single, unbroken family tree stretching back 600 million years. There are many more examples of our connection and unity from science. But the bottom line here is that we are the earth. We're inseparable from it. We're made of it, by it, and for it. The earth is up here giving this talk this afternoon, and the earth is sitting in those earthen chairs listening. It's just one thing. We and it are us. One life. One universe. The essence of one is that you are neither separate nor even separable from other people, other creatures, the earth, ancient stars, or the universe itself. Indistinguishably one. You are the universe. Come alive. Recently, I've been trying to visualize myself, meditating on myself as a drop of water flung from an ocean wave, in the air and seemingly separate just for a moment, but always part of a process unfathomably more powerful, more ancient, and deeply mysterious. The poet Rumi wrote, "You are not a drop in the ocean. You are the entire ocean in a drop." Now I want to go back through the candles one at a time, but stepping back a little bit and seeing if we can see threads of spirituality that run through them. Discerning our place in the universe, grasping for anchor points and finding none. Learning the first origins of our bodies. Exploring the illusions at the heart of reality, the dreams that stuff is made of, if you're a Shakespeare fan. The interconnections of life and death, virtue and vice, cooperation and competition. Exploring the role of creation in a self-assembling universe. The oneness of all life, even all things. These are spiritual considerations. Do you agree? Science and spirituality are not opposites. For me, they're intimate partners, inseparable and deeply in love. So as you leave here today, I hope you will remember that you are both central and diffuse, temporary and ancient, flawed and fine-tuned, creation and creator, certainty and mystery. We are the universe, become conscious, glimpsing our vast and ancient self for the first time and wondering, what will we create next? Thank you. Really honored that you came. And again, big thanks to John and Joe and ASK people from